We use stoichiometry when we want to change information about one chemical into another. There are 3 steps to stoichiometry. Step number 1, change whatever information you're given into moles of the chemical that you have. Step number 2, convert that into the chemical you want by using a conversion factor. Remember, you set this up by timesing by what you want and dividing by what you already have. And then step 3, change that number of moles into the answer that you need. So this could either be in grams of a solid, volume or concentration of a solution, or pressure or volume or temperature of a gas, depending on the experiment you're doing. So for our first example, we have a balanced chemical equation, and we're asked to change 3.0 moles of oxygen gas into moles of water. So because we're already in moles, I can do a mole ratio into water and answer the question. So I set that up as a conversion factor. I'm going to times by what I want. So I want water. I have oxygen. And then looking at my balanced chemical equation, there is a 2 in front of the water. And there's no number in front of the oxygen. So that means that there's a 1 there. So that means I have a 2 to 1 mole ratio. And the way conversion factors work, remember, is that what you want to get rid of cancels out. So here I have oxygen divided by oxygen. So the only chemical I'm left with is water, which is what the chemical asked me in. And I'm going to be in moles of water. So this will give me my question. So if I take 3 and times it by 2 and divide it by 1, that gives me 6.0 moles of water. So now for a full Stoic problem here. You always want to start with a balanced chemical equation. So I'm going to be reacting magnesium with excess cobalt 2 chloride. So first step, change those names into formulas. Cobalt's got a 2 plus and chlorine's got a 1 minus. And then this looks like it's going to be a single displacement reaction. So my magnesium is going to go with my chlorine. And I have to re-crisscross that formula. The magnesium's got a 2 plus, chlorine's got a 1 minus. And the cobalt is left out all on its own. So put my states in. And this equation already looks balanced. As an organizational trick, it's really handy to write down the numbers in the question underneath the corresponding chemical and what you're actually trying to find. So here, if I start with 5 grams of magnesium and react it with excess cobalt 2 chloride, the excess means that my magnesium is my limiting reactant. It asks me how many grams of solid cobalt will theoretically be collected. In order to go from grams of magnesium to grams of cobalt, I need to go through moles. So my first step is to take my 5 grams and divide it by the molar mass of magnesium to get me moles. So that gives me 0.206 moles of magnesium. Now to go from magnesium over to cobalt, I have to times by a mole ratio. And so there's 1 cobalt for every 1 magnesium. So that gives me 0.206 moles of cobalt. If I want to change that into grams and answer the question, I'm going to multiply that by the molar mass of cobalt, which is 58.93 grams per mole, which will give me 12 grams as my final answer. Here's an example where it doesn't tell us what the limiting reactant is, and we need to find it on our own mathematically. So let's start by writing a balanced chemical equation. We need to react aluminum with hydrochloric acid. Now let's get a little bit more space. So Al plus HCl, that's going to be another single displacement reaction. My aluminum is going to go with the chlorine and make AlCl3, and hydrogen gas gets kicked out on its own as an H2. And I need some states. And I need to balance. So I'm going to end up needing a 6 here and a 3 here, a 2 and a 2. And that should get me balanced. To organize our numbers, the question says that I've got 17.5 grams of aluminum. I'm going to mix that with 250 mils of 12 mole per liter hydrochloric acid, and it's asking me what volume of hydrogen gas gets made when I'm at SATP. So that would be 100 kPa and 25 degrees Celsius, so 298 Kelvin. Okay, so you notice that I have complete information about both of my reactants. I need to figure out which is mixed in the lesser amount in order to use that as my limiting reactant. So I need to change them into both moles of the same chemical. Now it only makes sense to change them into both moles of hydrogen gas, because that's what the question's asking me about anyway. So if I start off with the aluminum first, in order to take my 17.5 grams and change it into moles, I have to divide by the molar mass, which is 26.98 grams per mole. And that gives me 0.649 moles of aluminum. To change that into hydrogen, I need to times by a 3 to 2 mole ratio, and so that gives me 0.973 moles of hydrogen gas. Now, if I do the hydrochloric acid, it's going to be, to get moles, it's the concentration times the volume in liters. So that gives me 3.0 moles of HCl. And in order to go from HCl to H2, I need to times by a 3 to 6 ratio, which gives me 1.5 moles. To figure out which is the limiting reactant, you compare your two new numbers. Since this number is smaller, if we follow back, it means aluminum is our limiting reactant. It was present in the smaller amount. So now, any other question I need to answer has to be answered using my aluminum amount. So the question asked me to find the volume of the H2 gas at SATP. So because this is a gas, I have to use ideal gas law. So I'm going to start out with PV equals nRT, and I know my pressure is 100 kPa, what volume do I have? If I've got 0.973 moles, and R equals 8.314, and my temperature is 298 Kelvin. And if I rearrange for V and take sig digs into account, I get 94.1 liters as my final answer. Now, 94.1 liters is the amount of hydrogen gas you can get if everything runs perfectly. All your reactants reacts, there's no left over, and none of the hydrogen gas that you made escapes your collection container. In real life, that really doesn't happen. So here's a follow-up question. If only 78 mils, oh, I think that's a mistake. Let's change that into liters. If only 78 liters of hydrogen gas is collected, what's the percent yield? So here's the equation for percent yield. It's the actual yield, which is how much you really collect, divided by the theoretical yield, which is how much stoichiometry told you should get. And then in order to make it a percentage, you times it by 100. So in this question here, my actual is 78 liters. My theoretical, Stoich told me I should have made 94.1 liters. Times that by 100 means that my reaction was 83% efficient. I got 83% of the product that I should have gotten.